Thank you. Thanks everyone for joining, and thanks Sandra for doing this talk. So one of the aim of the BWC is to educate, to increase the knowledge of the community of new topics, and definitely quantum is one of the buzzwords that we hear about, that we'd like to demystify and to know more about it, whether we are from a technical background or a non-technical background. So, Sandra, without further ado, I'll hand over to you. Thank you.
Thank you so much, Leila. Hi, everyone. Welcome. Thank you all for joining. My name is Sandra Soueid, and I'm excited to be here to talk about a favorite subject and passion of mine, quantum computing. This is The Future is Quantum, where I'll be giving you all an overarching introduction to the world of quantum computing. So let's get started, shall we? What is quantum computing? I mean, that's what you're here to find out, right? Maybe you've heard about quantum computing already and you want to know what the latest status of the research is, or you want to know what the implications of an existing universal quantum computer would be. Or maybe quantum computing is completely new and foreign to you. Perhaps it's a phrase you've encountered and you're curious. What is quantum computing at all? Well, I'm hoping to answer all of these questions for you all today. Allow me to start with the first. What is quantum computing? The study of quantum computing is the ongoing research and developing of creating a new class of computers that are centered around the principles of quantum theory. Our current class of computers, in contrast, would be called classical computers because they're based on different principles in physics than what a quantum computer would use. Whether you're tuning into this talk from your PC, MacBook, iPad, laptop, or Zoom on your smartphone, you're using some kind of classical computer to do it. And from now on, I'll keep referring to these computers as classical, by the way. And if you remember the state of phones and classical computers from 20 years ago, you'll quickly realize just how far they've progressed computationally within the past 20 years. Quantum computing is the next step.
Of what?
Could everyone please mute? So quantum computing harnesses the phenomena of quantum mechanics to deliver a huge leap forward in computation to solve certain problems. That's because for some problems, even the world's most powerful supercomputers just aren't that super. These problems are typically combinatorics problems. For example, say I'm planning my wedding and at every table I want to seat 10 guests. But I know that certain people just won't get along with other people, and I know there's just one perfect way to seat everybody to keep them all happy. I could find that optimal seating arrangement if I think about it, but I'm busy and I want to see what if a computer can think about it for me. So for just 10 people, to find the perfect seating arrangement at a table, there are more than 3.5 million total combinations of how to seat them. And if it takes a computer 1 microsecond to compute each of those possible combinations, it would take like 3.6 seconds to find the perfect arrangement. But I'm Mediterranean, and I'm gonna have more than 10 people at my wedding. So if I wanted to do this for 100 people to find the perfect seating arrangement, it would take a measly, 21 years to compute that perfect seating arrangement using a supercomputer. And that's just because supercomputers don't have the working memory to hold the myriad combinations of real-world problems like these. Supercomputers have to analyze each combination one after another, which can take a long time. Quantum computers aren't held by the same constraints. As the size of these hard problems scale, they become impossible to compute on our classical computers with currently known algorithms. A combinatorics problem like the dinner table one I just mentioned could, at scale, literally take the age of the universe to compute. But with already known algorithms for a quantum computer, solving at scale could take mere minutes. This paves the way for a multitude of applications for quantum computing and opens up some amazing possibilities. These potential applications fit into these archetypes: quantum simulation, quantum linear algebra for AI and machine learning, and quantum optimization and search. Quantum simulation is simulating things like chemical reactions or how electrons behave with different materials with a quantum computer. Here, quantum computers have an exponential speedup over classical computers because classical computers have a hard time simulating quantum systems. One such system would be studying chemical reactions to improve their efficiency. One use case would be producing fertilizer in a way that emits way less carbon dioxide, since current production contributes to 2% of global CO2 emissions. We can use quantum simulation to improve batteries, develop drugs, investigate new chemicals and new materials, and we can do so by rapidly prototyping many different materials instead of physically making them and testing them in a lab, which would save a lot of money and a lot of time. These are the kinds of problems that quantum computers would be well suited to solve. Additionally, quantum computing's anticipated ability to solve today's impossibly complex logistic optimization problems could drive considerable cost savings and carbon footprint reduction. For example, consider improving the global routes of the trillion-dollar shipping industry. If quantum computing could improve container utilization and shipping volumes by even a small fraction, this could save shippers hundreds of millions of dollars. All of these potential applications are very exciting, and we should be excited. But to avoid falling into a dangerous trap by misunderstanding what quantum is better suited for, I wanted to address some of the hype around quantum and better explain what quantum advantage is and what it isn't. So maybe you've heard some of these before. I'll be going through a few slides now. So maybe you've heard that quantum computers will replace all classical computers. This is a myth. Quantum computers have benefits over classical computers for solving certain problems, but classical computers aren't going anywhere. They're a lot cheaper, very powerful, and the use cases that quantum computing can solve are generally too niche for the everyday computer need. Maybe you've also heard this one. This is a really pervasive one. Quantum computers try all possible answers in parallel, and that's how they achieve such enormous speedups over classical computers. This is also inaccurate. Later on in this talk, you'll find out more about how quantum algorithms choreograph quantum circuits to get the highest probability of resolving to the correct answer. It isn't a matter of trying infinite possibilities in parallel at once. And this one might be painful for some of you. Quantum computing is always 20 years away. Well, I can't tell you for certain if this is just a myth or not, but I'd like to take a pause right here and give a quick sidebar. So a dear friend of mine recommended a book to me recently called How to Invent Everything. And the premise of that book is you're a time traveler and you've been dropped somewhere along the timeline of the world's history from the dawn of the universe to today. How can you recreate all of our present technology from the point you've been dropped off in? I thought that was a really interesting concept, and I figured, well, that's just present technology. What about the future? So let's find out ourselves what 20 years away can look like. Starting now, all of you in this Zoom call are time travelers. And we're going to the year 2042. Let me set the scene. So somewhere, could be New York, could be London, could be Paris, Mars. We're all living in a waste-free, incredibly efficient society. Since the advent of quantum computers, we found new, sustainable materials. We've optimized our food, waste, and transportation systems, and have brought our dangerous greenhouse gas emissions down immensely. With new drug discovery and personalized medicine, diseases are almost completely nil. It's basically a utopia. And you live in this utopia, and you're on your way home when your phone starts buzzing. Bzz, 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 bzz. That's what phones sound like. And it's been a long work week, you know. Your friends are calling you, you pick up, they're asking you to hang out. It's been a long week. It's Monday. They really want to try out the newest extended quantum battery life upgrade on their Iron Man suits. And they'd really love it if you could join for a quick fly around town at sunset. So, of course, you want to fly. That's the best part about living in 2042. You say yes, you'll see them then. But you've got some time before sunset, though, so you head back to your place, and crash for a bit. You're just getting settled when boop, boop, boop. The most annoying alarm goes off in your apartment complex. Boop, boop, boop. Aw, man. Ah, geez. You hate these. You turn to your TV to see what cumbersome message awaits you. Emergency. A case of COVID-42 was detected in your building. Please quarantine immediately. Antidotes will be administered in 1 to 3 days. Virus schematic available online. Aw, man. That sucks. You just made plans with your friends, and now there's some stupid virus ruining your fun. What are you gonna do? Stay stuck inside? Well, my friends, this is the future. You don't have to quarantine if you're cured. You don't have to wait 1 to 3 days for the local scientists and doctors to make your cure either. You can use a quantum computer to make your own. I mean, granted, it's only 20 years in the future, so not everyone has a quantum computer yet. But you're not everyone. You've just moved into this apartment though, so you haven't set up yours yet, but you definitely have everything you need to make a quantum computer. And look, you even have your instruction manual on hand to get you started. So, are you ready? Can you build a quantum computer in time to make an antidote and get out with your friends before sunset? Of course you can. Let's get it. You open your manual and you turn to the first page and you see the schematic. And truthfully, it confuses you a bit. You haven't looked at something like this in a while, but you don't let it overwhelm you. You do what your great teachers have always taught you to do. You break it down. So you read the schematic from the bottom up and you start with the very building blocks. And the biggest building block of them all, the foundation of what builds out a quantum computer, is staring you right in the face. It's qubits. So you start there. You remember, if there's anything you need to learn, it's this. A qubit, which stands for a quantum bit, is the basic unit that stores information in a quantum computer. The classical computer analog is a classical bit, which can be either a 1 or a 0. But basically, a quantum bit, on the other hand, can be in this multitude of states in the state of 1 and 0. This is called superposition. It's the state of the unknown until it's measured. So I kind of use this as an excuse for donuts, but let's say the frosted side of this donut is a 1 and the unfrosted side is a 0. Where a classical bit can be a 1 or a 0, a quantum bit can just be like a spinning donut, just in multiple states at once. And you can't really tell if it's which state it's on until you decide to measure it and make it stop. Qubits are very special because of this property of superposition, as well as entanglement and interference. And they combine these 3 quantum phenomena to create a whole new paradigm for computing. To tell you a bit more about superposition, it's what it is more specifically is the linear combination of the 0 state and the 1 state, and with probabilities assigned to the likelihood of each of these states. So if I'm in a state of superposition where I have a 50% chance of measuring out to a 0, or a frosted side, and a 50% chance of measuring out to one side, then I can expect if I run 10 trials, I'm going to get 5 zeros and 5 ones. The benefits of superposition are that it offers many states at once, and as you get many qubits in a state of superposition, you open up the possibilities to parallel operations and exponential multiplication. Another nifty thing about qubits is their ability to be entangled together, and entanglement is when qubits are connected to form multi-qubit quantum states. So if I have 2 donuts and I entangle them together like those fancy atoms on my screen, then their destinies become intertwined. And if I want to, and if they're in superposition, just spinning around and stuff, and I want to measure 1, I'll collapse the superposition for both of them, and I'll have to measure the value of both of the qubits at once. So the cool thing about entanglement is that it contains more information than a single qubit. You have this multi-qubit state. And with just using two qubits, we can get this probability distribution. You see in these spheres that In the previous slide, the arrow was pointing just straight to indicate 50% probability of each likelihood, but there's more information here than just 50%, 50%. Here we have a whole probability distribution of what the possible outcomes can be. Another cool thing about entanglement is that it works over a really large distance. So my qubits can be very close together or very far apart. I could have a qubit here and a qubit on Mars, and they'll still stay entangled. It opens up some interesting questions, this entanglement piece, because you might start to think, oh, if I have a qubit here and a qubit on Mars, can I talk to my qubit on Mars? But you would be constrained by some overhead of classical communication, but who knows, the possibilities are pretty interesting, huh? And lastly, a very important piece of using qubits to build quantum computers is to utilize interference of qubit to qubit interactions. So we've been looking at the qubit as either a donut or the sphere of probability, but mathematically it can be just transcribed by a wave function. And these wave functions can interact with each other in a way that can reinforce or diminish each other. And you can use that to control the probability and bias a measurement towards the result that you intend. What do I mean by this? So when I say that a wave function can reinforce itself, then if you have multiple waves that with positive amplitudes, they can add up in a constructive way. If you have a positive and a negative amplitude, they can cancel each other out. So this is kind of how noise canceling headphones work. If you have ambient noise with a positive amplitude and your noise canceling headphones emit a negative amplitude, the two amplitudes interfere destructively and cancel each other out. So the amplitude is 0 and the noise is canceled. The event doesn't happen at all. So we use this property to make results that we don't want destruct and results that we do want to be amplified, and the probabilities of reaching those results to get amplified. And we can use all these properties of superposition, entanglement, and interference all together to get the desired outcome we want. Now that we know the quantum properties that make up a qubit, it's time to choose a real manifestation of one for your quantum computer. At the time of your instruction manual, 2022, superconducting qubits were the most popular approach. Superconducting qubits are made from superconducting wires with a break in the superconductor called a Josephson junction. The most popular type is called a transmon, where the two energy level system is encoded in pairs of the electric charge moving across the junction. There are other designs that use magnetic flux in a loop of wire or the phase across a wire as the two-level system. We can also make qubits out of other fundamental entities like atoms, electrons, or photons. And one example of using photons is this linear optical qubit, which uses photons of light as the qubit. And the qubits are operated on using optical elements such as mirrors, wave plates, and interferometers. And they're printed onto these integrated photonics chips. The two-level system can be either a superposition of paths that the photon takes, or a superposition of different numbers of photons present in the path. And lastly, although there are many, many more qubits and many more technologies out there, is this trapped ion technology, which uses charged atoms as the qubit. These atoms are ionized, having a missing electron, which makes them electrically charged, which means that they can be levitated or moved about with electromagnetic fields. Here, the two-level state that encodes the qubit are two specific energy levels of the atom, which can be manipulated or measured with microwaves or laser beams. Now, you live in 2042, so you're just going to choose the provably best qubit. And the best qubit is the one that overcomes the obstacles of making a qubit in the first place. First is noise. Noise can be from cosmic rays, radiation, heat energy, or rogue particles. And all of this noise can impact the state of your qubits and affect and skew your results, making all your computations gibberish. With too much noise, you won't be able to achieve accuracy in your results, and basically you'll just be outputting randomness. Another disadvantage is decoherence, which happens when your quantum information leaks away because of environmental factors. This happens because of interactions with the outside world. You want your qubits to be entangled with each other, but not entangled with anything else. However, you need physical stuff around your qubits to control them. You just have to protect them from entangling with the environment around it. And some amount of decoherence and noise is inevitable in any physical system. It gets worse the more qubits you have entangled with each other. And at the time of 2022, the time of this book, it was a big question to ask, will it ever be possible to make a large computer with a large number of qubits, or will decoherence and noise ruin everything? But in 2042, you've had that all sorted out already. But lastly, you want to consider scalability of your qubit. For each qubit, you need wires to manipulate and measure it. For a small number of qubits, this is manageable, but as qubit numbers increase, the amount of physical control you needed increases linearly, which is a massive engineering problem. So you take all this knowledge, you remember what a qubit is again, and you set up your monitor and your keyboard and an empty tower, and you decide to plop in your qubit of your choice in there, and you take a look back at the schematic. Great, you're 30% of the way there. What's next is working on the computer architecture. So computer architecture is going to be what builds out the quantum circuits of your quantum computer. So let's get started with quantum circuits, and they are computational routines consisting of quantum operations on quantum data, which is held in your qubits. And what a circuit looks like, this is a diagram, kind of looks like a composition, I would say, like a musical composition. But each horizontal line in a circuit represents a qubit, with the left end of the wire being the initial quantum data and the right being the final quantum data generated by the quantum circuit's computation. Quantum circuits enable a quantum computer to take in classical information and output a classical solution, leveraging the quantum principles we discussed earlier, such as interference, entanglement, and superposition, to perform the computation. So on that circuit diagram that I showed, you probably saw those blue and green and pink boxes, and those were to represent gates. And quantum gates are the building blocks of quantum circuits. And if you're familiar, they're like the classic logical gates that are used on digital circuits, but they have different functions. So this gate, the Hadamard gate, is a gate that puts a qubit into a state of superposition. So if I have a quantum bit on the left side of this gate, and I put it through a Hadamard gate, then it can start spinning, and it'll be in a state of superposition, an unknown probability. Well, not unknown, but another such box seen on that circuit diagram was the measurement operator, which, if I'm in a state of superposition, what a measurement operator does is it just forces me to take a measurement and stop and collapse the quantum state. So to give an overview of everything we've covered so far, we can get many qubits into a state of superposition and form this multi-qubit state that is a superposition of all possibilities. Then we can run a quantum circuit on this multi-qubit state, and we'll do so in a way that we use entanglement and interference to constructively interfere towards results we want and destructively interfere away from results we don't want. And then at the end, we'll take a measurement and we'll be left with the solution that we intend. Some other things to consider in the architecture are quantum error correction schemes. So this exists to fight decoherence and other noise, which is a large problem in building out quantum computers. One of the phases in building quantum computers includes fault-tolerant phases, and this is done by using many entangled qubits together to represent one noise-free qubit. Another crucial piece of your architecture is the compiler, and your compiler is tasked with optimizing the number of noisy operations to obtain the highest fidelity of encoded states with noisy gates. So knowing all that, you're ready to build your quantum chip, and you do that, and you plop it into your tower, but your computer still isn't happy. That's because you've gotten all the hardware done, but all you're missing is the algorithms that will take advantage of your quantum hardware. You're missing the instruction set. Your computer just doesn't know what to do with all this power it got. So there are many quantum algorithms, but you decide in the interest of time and meeting your friends at sunset that you're just going to focus on the two of the most famous and historically important. Theoretically, there are a bunch of problems you can solve that are thought to be intractable on classical computers. And one algorithm that came out to solve such a class of problems was Shor's algorithm that was created in 1994. And it was an algorithm that efficiently found factors of large integers. So on your computer or your calculator, using your smartphone, you can easily multiply two numbers, right? There's an easy, efficient classical algorithm for multiplication. But if you were to take that number and ask your computer, what are the factors that make up this number, it would be very difficult. And that's because the search base of possible factors is so large. There's no efficient classical algorithm and no way to get it. And actually, we use the basis of how difficult this problem is for a classical computer as the base for our encryption and how we send secure messages, secure like banking, financial data, everything that you do on the internet in a safe, secure way relies on the fact that this problem is difficult for a classical computer to solve. But in 1994, Peter Shor proved that it would be very easy to solve this problem on a quantum computer. It would take seconds what would take a classical computer thousands of years to do. So this made headlines because it was the first application of a real-world problem with real-world security implications. Another famous and popular algorithm is Grover's algorithm. This is not as dramatic as Shor's algorithm, but still has interesting potential applications because while Shor's algorithm provided an exponential speedup over classical solutions, Grover's algorithm provides a quadratic speedup. And in 1996, this algorithm came out as a way to search an unstructured, unsorted database. So if you just had, if the goal here is to find the number 42, in a classical computer, you would have to search each unit of this array, or you would have to search your entire database until you found the number you were searching for. But using a classical computer, you could cut that runtime. Or using a quantum computer, you can cut that runtime using some of the tricks such as interference and entanglement that I mentioned earlier. And this is really useful for large amounts of unordered data. So as Internet of Things and sensor data and just anyone who's familiar with big unstructured, unordered data, as the number of data points gets large, then this speed up is significant. And that's it. You've figured it all out. You've programmed your computer. Your computer looks nice and happy. So you run your quantum algorithms and start synthesizing an antidote. And yay, congratulations. You made it. You weren't about to let some silly virus ruin your fun, you know? We're humans, we persevere, we go out flying with our friends after work, easy peasy. So thank you all for making it with me this far. And I'd like to take us back to the present, the year 2022. And I'd like to say that as fun as that was, it's not as far-fetched as it seems. There's a lot of movement right now going on in the quantum computing ecosphere, and this graphic illustrates just some of the key contributors to the quantum computing ecosystem. At the bottom of the stack, we have the hardware companies who build physical quantum computers. There are many different ways to build a quantum computer, and this depends on the type of qubit technology used by each company. And we covered a few of them today, the superconducting ones, trapped ion, photonics. We didn't cover silicon, but there are even more. And quantum hardware companies are currently trying to scale up their quantum computers and include enough error-corrected qubits to reach quantum advantage. We don't yet know which type of hardware will win the race and be able to run commercially relevant applications, though. So further up the stack, we have quantum software companies which develop products that utilize quantum hardware to run algorithms. The software products can be used by researchers and enterprise customers for applications such as drug discovery and battery and material screening and cryptography and finance. And at the top of the image, we have enterprise customers and quantum startups that specialize in particular applications. For example, Protein Cure that does protein folding and for drug discovery. Tech giants like Google and IBM and Amazon are big players in the quantum race. In October 2019, Google claimed to have reached quantum advantage by demonstrating a calculation on their quantum computer that was intractable on a classical computer. And the following graphs are all sourced from McKinsey's end of 2021 report on quantum computing use cases. If you see in this graph, in the last 5 years, more than 150 quantum computing startups and university spinouts and research groups have been formed across the globe. And in the past couple of years, $1.7 billion of private investment has poured into the industry, with a total of 227 funding rounds. And over 70% of this total investment is allocated to the hardware players, since we're still trying to figure out what is going to be that 2042 qubit, what is going to be the winning one. Also, this is not exhaustive. Some of the activity is opaque and we don't know what the real numbers are. This is just what's publicly available. Speaking of public, there's a lot of public investment as well into quantum computing, with China taking the lead at $15 billion planned into their quantum computing programs. The US in third place with $1.3 billion. And this chart shows the value at stake should a quantum computer exist. I hope I gave you a taste of what it would be like if a quantum computer existed, but basically, most known use cases fit into 4 archetypes: quantum simulation, quantum machine learning, quantum optimization, and quantum factorization. And by focusing on potential use cases in a few industries, research suggests could reap the greatest short-term benefits from the technology, such as chemicals, pharmaceuticals, automotive, and financial industries. Collectively and conservatively, according to McKinsey, the value at stake for these industries could be roughly between $300 billion and $700 billion. Quantum computing use cases in finance are a bit further in the future, since they require a larger number of qubits and might not benefit so much from the short term. However, the use case is still speculative, but however, we believe that the most promising use case of quantum computing in finance are in portfolio and risk management. For example, efficiently quantum optimized loan portfolios that focus on collateral could allow lenders to improve their offerings, possibly lowering interest rates and freeing up capital. As of 2021, the global lending market stands at $6.9 trillion, so that suggests a significant potential impact from quantum optimization. And these charts are estimating 2035, so even sooner than our future rendezvous. And lastly, last chart at least, this is a timeline of the stages of quantum computing, where right now we're in this early stage. Google has proved quantum supremacy by doing this certified randomness test. And we're at the stage where maybe we have about 100 qubits or so. But as that number grows and we see 100,000 qubits, then we'll get into applications such as protein folding. If we get to 1 million qubits, we'll get into this solid material simulation, supply chain optimization. And when we get to a universal quantum supercomputer, and we're in the tens of millions of qubits, we can see personalized medicines, automated drug recommendations, self-driving robots, and so many more applications. So I'll conclude this talk with a favorite quote of mine by one of the most inspirational physicists of all time, Richard Feynman, who said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum." It is human nature to persevere, to push our limits of understanding and knowledge. We know it's possible, we've proven it, and we've never stopped just shy of making it a reality. The world will benefit from a quantum computer, so we better make it. Thank you, everyone.